Did you see the sentence?
Okay, hello everyone. Okay, this is slow to load, but I'll get it here. Okay. Okay, I'll give that just a minute to load here. And oops, sorry, wrong one. This one here. Yeah, this one. Okay, I'm going to share my screen. Okay, looks like no one else is waiting to enter, so we'll go ahead and get started. Okay, can everyone see the screen? All right. So today we'll should be able to complete our discussion of alkanes and cycloalkanes. Okay, so to review some of the main points, we talked about constitutional isomers where the connectivity of atoms is different, where there's a different skeleton. Here's one example. As the number of carbon atoms goes up, the number of constitutional isomers that are possible goes up significantly. Okay, so as a result, it's been necessary to come up with a systematic method of naming, okay, which we spent quite a bit of time on the last couple of lectures. These are the substituents: methyl, ethyl, propyl, isopropyl, and then there's 4 butyl groups. Right, and then these are the parent compounds. Make sure you know the names of the first 10. Substituents are located by position numbers. We want to give the lowest combination of numbers to the various substituents. Every substituent gets a number, even the same substituent on the same carbon. Okay, so this is 4-ethyl 2,2-dimethyl hexane. Classification of carbons. Again, make sure you're aware of that. That will become important later with other functional groups. Okay, cyclic alkanes. Okay, for a monosubstituted cycloalkane, we don't need a position number, and the parent will have the prefix cyclo. I'm going to skip over this. We introduced the idea of torsional strain, okay, where hydrogens are eclipsed. Okay, and that's the case with cyclopentane when it's in the planar conformation. Okay, there's repulsion between these hydrogens, and that introduces strain on this bond. Okay, this can be relieved by a puckered envelope conformation or a folding of the ring. The most stable conformation of cyclohexane, the six-membered ring, is what we call the chair. The chair has these four carbons in the same plane. There's one below and then one above. And the chair undergoes a continuous folding and flipping. Continuous folding and flipping at room temperature. It goes from one chair to the other. In the chair form of cyclohexane, you have 6 hydrogens which are axial, that is straight up and down, and then you have 6 that are equatorial, okay, basically horizontal. Okay, in the boat conformation of cyclohexane, you also have what is called steric strain between these flagpole hydrogens. Okay, they're not bonded to each other, they're remote from each other, but in three-dimensional space, they're close enough where repulsion occurs. Okay, when you have a substituted cyclohexane ring, general rule is there's more room in the equatorial position than there is in the axial. You have a continuous equilibrium that occurs between, for example, this methyl being equatorial and being axial. Okay, then we also talked about cis-trans isomers. These are distinct from constitutional isomers. Constitutional isomers would be, for example, 1,1-dimethyl cyclopentane and 1,2-dimethyl cyclopentane. Cis-trans or geometric isomers have the same substituents on the same position, but they have a different three-dimensional geometry. Okay, up here at the top, we have the cis isomer. Okay, where both methyls are on the same side. And here we have the trans. Okay, not all disubstituted cycloalkanes will exhibit cis-trans isomerism. Okay, this is another way to represent cis and trans. Okay, we can have both methyls going back, or we can have one back and one forward for the trans. Okay, so here's the hexagon form of cyclohexane, showing the cis and trans 1,4-dimethyl. Okay, these are both trans isomers. What was axial became equatorial. What was axial on this position also became equatorial. And so this is the more stable, lower energy conformation in which both methyl groups are equatorial. Okay, with the cis isomer, we have one axial, one equatorial. Okay, remember with the trans, we had, for this one, both of them were axial. So to make the cis, we actually had to break this bond and place the methyl down here. Okay, this is cis because Okay, hydrogen's on top, methyl's on bottom. Okay, over here, hydrogen's on the top, methyl's on the bottom. Okay, so that's how you can recognize that it's cis. Okay, it's oftentimes the first time you look at it, it's not obvious that this is a cis isomer. Okay, when we do the ring flip, okay, what was axial became equatorial, what was equatorial became axial. Okay, so in both of these forms, we have one axial, one equatorial, so they're equal stability, okay, unlike the trans, 1,4. Okay, I'm going to skip over this one. Okay, let's go ahead and take a look at this problem here. Okay, so it says to draw the alternative chair conformations. Okay, so to draw the chair, we make two offset parallel lines. Okay, we have one carbon above to the left, we have one carbon below to the right. For the axial, I start down here at the lower right corner, go down, up, down, up, down, up. All right, equatorial, this bond should be parallel to the second bond over. This one would be parallel to this bond. This one would be parallel to this bond. And the three on the right point to the right for equatorial, the three on the left point to the left. Okay, so this one needs to be parallel to this one. This one needs to be parallel to this one. And this one is parallel to the second one over this one. Okay, so this is the 1,4 cis for part A. Okay, so I'm going to draw another chair over here. Okay, so 1,4 cis. I can start anywhere. I'll call this position 1. Okay, so I'll put an OH here and an H here. Okay, so OH is on top. You go 1, 2, 3, 4. And for the cis, OH would again be on top. Hydrogen is on the bottom. Okay, so that would be the alternative chair, and then these other positions would all be hydrogens. Okay, and then there's another way in which we can write that. We could have both OHs on the bottom, okay, like this. Okay, and that would also be the other equilibrium form for this dialcohol. Okay, for part B, that's the 1,3 cis. Okay, so I'm going to go over here to position 3, and OH is on top, and OH is on top here. Okay, and then on this one, OH is on the bottom, OH is on the bottom. Okay, so these are two equilibrium forms. Both OH is on top or both OH is on the bottom. Okay, here they're both equatorial, and over there they're both axial. Okay, so this would be the more stable form, but both of these would exist at room temperature. They would equilibrate back and forth. This is the lower energy form where both groups are equatorial. Okay, let's go ahead and look at part C. Okay, so for part C, okay, I'm going to go ahead and erase these OH groups. We'll start over. Okay, I'm going to, okay, for this one, I'm going to start here with the methyl. Okay, so I'll put the methyl on top. And, okay, so we have a alcohol on 3 and one on 4, if I'm calling this number 1. Okay, so 1, 2, 3, and okay, methyl's on top, so the alcohol would be on top, and the next alcohol would be on the bottom. Okay, so this methyl and this alcohol are cis to each other. They're both on top. This alcohol and that alcohol are trans to each other. Okay, this one's on top, this one's on the bottom. And that's exactly what the cyclohexane ring shows, the hexagon shows on the slide. Okay, alternatively, okay, we could switch all 3 of these. Okay, put methyl on the bottom, this OH on the bottom, and then this one OH on the top, and it would be the same compound. Okay, so for part D, okay, let's call the carbon with the OH on the right, let's call that number 1. So we have OH on top, like that. Then we go over to the 3rd carbon, and then on top we have a CH2OH. And then that's on top, and then let's see, the next carbon over, we have an OH on the bottom. I'll show that each here. Okay, so OH is on the lower position. So hydrogen would be on top. And then we have an OH on top, like that. Okay, and then 2 H's on this position. Okay, so that would be the alternative chair for part D. Okay, before we look at physical properties, I want to talk a little bit about bond angle strain. We've talked about torsional strain. The smallest cycloalkane is cyclopropane, okay, in which we have 3 carbons connected in a triangular pattern. Okay, since all 3 carbons have to be in the same plane, folding of the ring is not possible. The hydrogens, every one of the hydrogens has no choice but to be eclipsed. And so you're going to have torsional strain on this bond because of hydrogen-hydrogen repulsion. Okay, we have another type of strain, and that's called bond angle strain that takes place. Okay, for a tetrahedral carbon, right, the bond angles are 109.5 degrees. Okay, in an equilateral triangle, the angles are 60 degrees. So there's a lot of distortion that occurs. As a result, cyclopropane, propane 3 carbons, is more reactive than other alkanes. Okay, and it undergoes reactions in which the ring opens up. I'm going to make a model of cyclopropane. Okay, I'm going to try to zoom in here. Wrong way. Okay, so here's propane, and each carbon is tetrahedral. And if I try to form a 3-membered ring, okay, but I've actually broken some of these model pieces doing that. Okay, you might be able to see that there's bulging in these bonds. There's distortion from the ideal tetrahedral bond angles. Okay, and so a lot of energy is released as this ring breaks open. Okay, so that's called bond angle strain. So cyclopropane exhibits both torsional strain because of eclipsing of hydrogens and bond angle strain. Okay, let's look at cyclobutane next. Right, in cyclobutane, we have a 4-membered ring. And in a square, bond angles are 90 degrees. All right, so there is bond angle strain that occurs in a 4-membered ring in a cyclobutane. And it does take a little bit of effort in order to make a cyclic 4-membered ring here. And you might be able to see that there is some bond strain, there's some bulging in these bonds, not as much as with cyclopropane. In the planar conformation, okay, you have eclipsing of hydrogens, so there's torsional strain that occurs. But unlike cyclopropane, you can fold the 4-membered ring, and that relieves some of the bond angle strain and the torsional strain. Cyclopropane and cyclobutane rings do occur in nature, but they're much less common than other rings. 5- and 6-membered rings are actually very common. Larger rings are less common, but they do occur. Okay, now we'll look at physical properties. Alkanes are nonpolar compounds and have only weak interactions between their molecules. Okay, the only significant intermolecular force is London dispersion forces. And these are forces of attraction resulting from the interaction of temporary induced dipoles. All right, so methane is a nonpolar molecule. And as two methane molecules approach each other, there's a temporary shifting of the electron cloud from one side to the other. And this results in a weak interaction, a weak attractive interaction. Okay, we alluded to this when we're talking about petroleum refining. Low molecular weight alkanes, 1 to 4 carbons, are all gases at room temperature. Methane, propane, butane, also isobutane, they're all gases. From about 5 to 17 carbons, those are all liquids at room temperature. The higher molecular weight alkanes, 18 or more carbons, are white, waxy semi-solids at room temperature. Okay, so, and they represent such products as paraffin wax and petroleum jelly. Okay, because of the weak interaction between alkane molecules, they have low densities. Okay, in the liquid phase, especially in the solid phase, water has a density of 1 gram per milliliter. So liquid and solid alkanes will float on water. Constitutional isomers are different compounds, and they have different physical properties. Okay, and here's just one example. This is a space-filling model of hexane, and then this is 2,2-dimethylbutane. Okay, these have the same molecular formula. Go ahead and draw the structures of these on the board. That's hexane, and this is 2,2-dimethyl hexane, butane. 2,2-dimethyl butane. Okay, so these are the different isomers of C6H14. We have hexane listed first, and notice that when we have branching, that's going to lower the melting point and the boiling point. Okay, it won't have much effect on the density. We can see that the more branched isomers, especially 2,2-dimethylbutane, has a slightly lower density, but branching lowers the melting point and the boiling point. Okay, with hexane, you have greater surface area in contact. Okay, so if we line up another hexane molecule, like this, okay, you have all this surface area that's in contact to induce temporary dipoles. Okay, with something like 2,2-dimethylbutane, as these approach each other in the liquid or the solid phase, you can see that there's a lot less surface area in contact. And so there's a lot less London dispersion interaction. So that has the effect of lowering the boiling point. The main commercial use of alkanes is as energy sources. They undergo combustion, and the heat is used as a source of power. Okay, we can calculate the heat of the combustion using calorimetry. This is the heat released when 1 mole of the substance is oxidized to carbon dioxide and water. Okay, so down here we have the balanced equation for combustion of methane. Methane reacts with 2 equivalents of oxygen gas to produce carbon dioxide and 2 equivalents of water. Okay, this is exothermic. Minus 886 kJs per mole are released. With propane, okay, per mole of propane, you have quite a bit more heat released. Negative 2,220 kJs per mole. Okay, we also use more oxygen per mole of propane. Okay, these are the products that we can get from petroleum. Natural gas is about 90 to 95% methane. Most of the rest is ethane. It does contain smaller amounts of propane and butane. And then the liquid and solid portions of petroleum include gasoline, kerosene, fuel oil, lubricating oils, and at the refinery, these are separated by fractional distillation. Asphalt is the residue that doesn't distill off. Coal is also a source of alkanes. Okay, this is a fractioning tower. Gases come out the top, and then the different products come out at different boiling ranges. Okay, after the gases, we have gasoline, then kerosene, which is higher boiling, then fuel oil, and then lubricating oil. Coal, which is primarily carbon, can be converted to carbon monoxide by heating with oxygen or water. This is used to make other industrial products, okay, such as methanol and acetic acid. Right, in the United States, if the United States moves from a petroleum economy to a natural gas economy, as some advocate, synthesis gas and synthesis gas-derived methanol will become key building blocks. Okay, so that's it for chapter 3. We're going to get started on chapter 4 next. Go ahead and keep sharing my screen, and let's go to Canvas here. Chapter 4. Okay, I'm anticipating the test next week will cover up through chapter 3. Okay, so this material would be on the second test, not on the first test. I'm still working out the details of the test. I originally was going to have it on campus, but I don't think that's going to be practical. Okay, so in the next few minutes, we're going to start on the subject of alkenes and alkynes. Alkanes are what we call saturated hydrocarbons. Okay, that is, they're saturated with hydrogens. We can't hold any more hydrogens. Alkenes, alkynes, and also aromatic compounds are referred to as unsaturated. And these are compounds that contain one or more carbon-carbon double bonds or triple bonds, or in the case of aromatic compounds, benzene-like rings. Alkenes will contain a carbon-carbon double bond, and they'll have the general formula CnH2n. Okay, remember alkanes were CnH2n plus 2. So each time we form a double bond, we lose 2 hydrogens. When we form a triple bond, we'll lose 4 hydrogens. So for an alkyne, the general formula is CnH2n minus 2. Okay, this is the simplest alkene, which is ethene, and then the simplest alkyne is ethine. This is commonly called ethylene. This is commonly called acetylene. Okay, we'll have a whole entire chapter on arenes. That'll be chapter 9. But benzene, even though we show that with carbon-carbon double bonds, it doesn't react like alkenes. And we'll explain that why, the reason why when we come to chapter 9. Okay, we're going to introduce the idea of benzene rings as substituents at this point. A benzene ring as a substituent, okay, we can show that like this. We can show C6H5, that implies a benzene ring. And then pH is also symbolic of a benzene ring. pH comes from the word phenyl. This is what's called a phenyl group. Okay, benzene as a substituent is not a benzyl, but it's a phenyl. Okay, this is the simplest alkene, which is ethylene or ethene, and this is propene, 3-carbon alkene. Each carbon is sp2 hybridized, so it's trigonal planar. In ethylene, all 6 of these atoms are in the same plane. Bond angles are approximately 120. The CCH bond angle that's shown there is 121.7. Okay, so this bond angle would be a little bit smaller than 120, but they're all approximately 120. Right, according to the orbital overlap model, a double bond consists of one sigma bond formed by the overlap of sp2 hybrid orbitals and one pi bond formed by the overlap of parallel 2p orbitals. Rotating by 90 degrees breaks a pi bond. Okay, so we saw that with ethane, we could freely rotate, but with ethylene, which is shown here, okay, I don't have free rotation. Okay, as the model accurately depicts, this is rigid. I actually have to break the pi bond in order to have this undergo rotation. Okay, because of this restricted rotation about a carbon-carbon double bond, groups on the carbons of a double bond are either cis or trans to each other. Okay, so on the left we have cis 2-butene. I'll make a model of that. This is cis 2-butene. I'll see if I can zoom in. Okay, so here is cis 2-butene. And then to go to trans, I can't simply rotate. Okay, I actually have to break a bond and reform it up here. Right, so this is the trans isomer. Okay, those are geometric isomers. They're also called cis-trans isomers. Okay, they are different compounds. They have different properties, such as different melting points and boiling points. Okay, an alkyne will consist of a compound that has a carbon-carbon triple bond. And with an alkyne, we'll have one sigma bond between the two carbons, and then we'll have two pi bonds formed by the parallel overlap of two p orbitals. Okay, we'll just get started on nomenclature of alkenes. Okay, alkanes will end in ane, methane, ethane, propane, butane, pentane, and so on. Alkenes will end in ene. And we'll number the parent chain to give the first carbon of the double bond the lower number. And then we'll follow the IUPAC rules for numbering and naming substituents. Okay, so in this first example, we have a 6-carbon chain. Double bond is between 1 and 2. Okay, we want to give the double bond the lowest number, and so we start numbering at the lowest position of the double bond. So this becomes 1-hexene. It's also correct to call it hex 1-ene. Okay, and the second one, the double bond, takes priority over the methyl group. We give the double bond the lowest possible number. The other substituents will fall where they may. Okay, so this is 4-methyl 1-hexene. Okay, for this one, we want to name the parent not as the longest chain, but as the longest chain that contains both carbons of the double bond. Okay, so the longest chain is actually 1, 2, 3, 4, 5, 6, but the longest chain that contains both carbons of the double bond is actually 5. So the correct name here is 2-ethyl 3-methyl 1-pentene. Okay, we give the alkene the lowest number. Right here we have an alkyne. Okay, the suffix for alkynes is YNE. Okay, butane, which is 4 carbons, becomes butyne. And the triple bond is between 1 and 2, so it's 1-butyne. And we have a methyl on position 3. Okay, and then this one is 6,6-dimethyl-3-heptine. Okay, the triple bond gets the lower number, not the methyls. Okay, triple bond, double bond takes priority. Okay, and this will be the last slide for today. Some alkenes, particularly low molecular weight alkenes, are known almost exclusively by their common names, especially commercially. Ethene is the IUPAC, ethylene is the common. We have propene and propylene, and then 2-methylpropene is commonly called isobutylene. All right, so I'm going to go ahead and stop here. No class on Monday. I'll send out an invitation to everyone for Wednesday's Zoom, but I'll also hold class in the classroom, so you have your choice. You can come to class or watch it on Zoom. Okay, Friday will be Friday will be our test. Okay, and I'll have more to say about that. Okay, so I'm going to go ahead and end the class.